So Sebastian just got here, so I think we can begin.
Okay. Good. Put the last straddles. Okay. Thanks everybody for coming. This is going to be Rogerio's speaking qualifier. I guess no rules. It's just like a regular seminar. No, so you don't have to wait for questions till the end, but keep the questions and clarifications during the talk.
All right. Thank you for the introduction, Sebastian, and thank you all very much for being here. Today I'm going to present my research on a autonomous drone cinematographer, where we use artistic principles to create smooth, safe, occlusion-free trajectories for aerial filming. And first, I just want to thank my committee for being here, Sebastian, Simon, Sharia, and David, and thank you for all the inputs during last year. So I'm going to begin with a motivation behind this topic and also some of the related work. And so the act of recording images is something that's intrinsically human, and we have been doing this for millennia. And for a very long time, the only way to record images was using paintings. But then in 1816, the first camera was invented, and this has changed the way we do many activities in human life. But in this talk, I'm going to focus specifically on camera perspective and how it has evolved over time. Initially, people placed cameras either on top of tables or on tripods, and the kinds of images you got were usually on the horizontal level, and they were very static scenes. But then, when invention came up in 1907, it was the dolly. The dolly is basically a camera on a rail, a camera on wheels, that you can move in a particular direction. And this allows you to apply the notion of movement, of continuity, to an image, or in this case, of movies. Another very important invention that changed camera's perspective was the selfie stick. And like today, the selfie stick is kind of a joke. It became very popular, but it's actually quite an old invention. And supposedly, according to the internet, this was the first selfie ever taken in 1925. What's nice about the selfie stick, jokes apart, is that you allow the operator to have this to have this third-person perspective of him or herself in a very easy manner. And another big innovation that came about 50 years ago was the Steadicam, or the stabilized gimbal. And what's interesting about this is that you can, you're not constrained to rails like in the dolly when you're trying to move a camera, because the stabilization allows you to generate very visually appealing images while traveling in any direction. And the last thing I want to talk about, and actually the focus of this presentation, is on drones for filming. Because drones are a very interesting invention, that drones with cameras, because they take advantage of all these previous technological innovations into one single device. And they allow us to achieve viewpoints that have never been possible before. These are just a few examples of very nice footages obtained with drones. So you can see that we have these third view perspectives. We have very stabilized images. We can achieve motions without the constraint of rails. And we can film both landscapes, actors, moving objects in a very cheap, reliable, and safe way. And now, there are many applications where we can use drones or the images generated by drones. For example, we can record sports, both indoors and outdoors. We can record professional movies, recreational activities, any kind of social event. And these are applications where what matters is the resulting, the actual image produced by the drone. But we can also think of applications where what matters are the decisions we're going to make based on those images. So for applications like defense, security, you're going to, let's say, follow a target, and you're going to make decisions based on what you're seeing. Also, we can think of a very hot topic nowadays of smart cities. So you could use the images generated by drones to understand traffic patterns, the flow of people in the environment. But the act of filming with a drone is really hard. And it's hard because it's a very complicated system, and in practice you usually have multiple operators controlling one single drone. Usually one of the operators only controls the aircraft itself. You have a second operator that just controls the camera independently. And sometimes you even have a third operator that controls just the focal distance of the lenses. You also have very unintuitive controls. Usually those RC controllers are related to the attitude of the aircraft, but what actually matters when you're filming is how the image looks like on the screen. And a drone is inherently a system with multiple degrees of freedom, so it's hard to control in general. And there are many more challenges that come when you're trying to automate a system like this, because you have to take into account a lot of artistic principles into your motion plan, and these principles are usually in the mind of the director, of the operator of the camera, but you have to take them into account analytically. You also have to, so if you're filming moving scenes or moving objects or people, you have to take into account forecasts of what's going to happen next in the scene. And you have to do all this processing and decision making online and on board, which is non-trivial given that we have this small and non-powerful computers usually on top of drones. And now let's look at some related work that gives us the big picture of which area is the area of drone filming. The first one that we would think about is it's related to UAV applications, such as high-speed flight, formation flight, or inspection. But we also have to take into account aspects from computer graphics and arts, such as placing cameras on virtual environments, and also there's a lot of literature on the principles behind movie making, like in Hollywood settings, for example. And a third big area that intersects with those two is motion planning, because we have to take those artistic principles into account and generate feasible motion plans. And we also have to represent the environment around us somehow. And specifically on that intersection, on drone filming, we also find some work that has been done. There's a lot of work on keyframe navigation, or on the user interaction between those cameras and whoever is operating them, landmark navigation, and even some work on optimizing trajectories online for filming. But even though this previous works, they take a very nice step towards making these systems deployable in practice, there are still quite a few limitations. In terms of motion planning, many of these works, they only deal with offline planning, so you must have very scripted scenes. Or they sometimes plan without any notion of forecasts of what's going to happen next, so they have very reactive motions to changes. In terms of objective functions, some of these papers don't deal with avoiding obstacles at all, and most of them don't deal with the concept of occlusions generated by obstacles on your image. We also see very simplistic environment representations in most cases, where they treat all the objects in the environment only as ellipsoids, but in fact we have any kind of shapes for obstacles. And fourth, we see some limitations in terms of system setups. Most of these papers only deal with motion capture systems where you have a very accurate localization of your actor. But in practice, you have a lot of noise when you're trying to localize a person or a car, etc. in space. Or they only deal with very static or low-speed scenarios. And sort of based on these limitations that we see in previous work, we defined our objectives, our contributions in this paper, where in terms of motion planning, we want to plan motions online using forecasts of what's going to happen in the scene. In terms of objective, we want to avoid both obstacles and occlusions. We want to be able to represent obstacles of any shape, not only ellipsoidal shapes. And we want to be able to work in realistic, high-speed environments, being able to film any kind of actor, like people, bicycles, or cars. Now that we know our contributions, I'm going to explain to you our approach and give some results. And before I jump into the approach, I just want to show a quick video so you can understand what the system is doing in practice. So this is a fully autonomous shot taken with our system, and the drone identifies the actor's location. It's doing a circular movement around the actor. And I'll just pause for a second to highlight a few things. Given measurements of the actor's current position, we feed them to a motion, to an activity forecasting module that gives us, using a common filter, gives us this purple trajectory over here. That's an estimate of where the actor is going to be in the next 10 seconds. And given this forecast and the director's artistic principles, we calculate the blue trajectory that tells us where artistically we would like to be if there were no obstacles in the environment. In this case, we're circling around the moving actor. But you can see that the blue trajectory is either going to collide with the mountain at some points, or it's just or it's going to be occluded by the mountain. And that's why we plan for the red trajectory online that avoids colliding with obstacles and avoids being occluded. We can also handle different types of shots and actors. So in this case, I'm riding my bicycle. We're doing a right side shot. And you can see that the drone smoothly adapts to go to my right side, and it's avoiding this mountain and re-landing online. So now I'll talk about the actual system that we have. Before I go into the details, I just want to show you the inputs and outputs that we have. As inputs, we have the image from the camera, so it's a monocular image. We also have LiDAR information about the environment that creates the map. And just a disclaimer, for the results that you'll see in this presentation, we made an offline map. But as future work, we're already working on putting a LiDAR to map any kind of environment as we fly. And we also have the drone's state estimation gains from IMU and GPS. And as outputs, we can control the camera independently of the movement of the drone itself. And of course, we can control the drone. So let's look at the first big box. This is what we call the vision pipeline. And what we have happening here is from the monocular image from the camera, we detect the actor. So we get a bounding box of the actor, and then after the initial detection, we track this template over time in the next incoming frames at a higher frequency than the detection. And over here, you can see that we can control the gimbal to maintain the actor on the desired position on the screen. So even if the actor tries to move, we're going to actively control the gimbal to keep him, let's say, centered, or you can use other artistic principles for that. Also, after we have a bounding box of the actor, we do two things in parallel. The first one is what we call ray casting. So we project a ray. Usually you can say the bottom of the bounding box, which corresponds to the feet of the actor. We project this ray onto the ground plane, so we get an estimate, a measurement of where the actor is at this moment in word coordinates. And we also have a module that estimates the heading direction of the actor, because this matters a lot for cinematography. If you want to do a right side shot, you have to know what is the right side of my actor, for example. And we feed this into the motion forecasting module that gives us that prediction. The second big part of our system is what we call the planning pipeline. And given the actor's motion forecast, and the map and the drone's state, we calculate a trajectory, and then we follow this trajectory using our drone. And now I'm going to explain to you a few of the most important pieces of this system. So the first one is the actor detection and tracking module. The first thing that we do is we get this image, this molecular image from the camera, and then we process it with a custom trained neural network. It uses the mobile net architecture to get some features of this image, and then a YOLO detector that gives us the most likely bounding box around the actor. And this operation takes about half a second on our onboard computer. After we get this initial bounding box, then we just, since this operation takes a while to detect the bounding box, we just track that template over time in the next incoming frames with a KCF filter. And lastly, we actively control the gimbal to keep the actor on the desired screen position. After we get this bounding box, you can see after the detection and tracking, we have those two modules happening in parallel, so the ray casting and this heading estimation module. And here, we regress the image from the bounding box into a heading angle for this actor. And there was a lot of interesting things in this work, because we have there's not an actual aerial data set with heading directions labeled, so we had to create our own data set. Then we faced this issue of obtaining enough training data for the system, and that's why we used both the labeled losses to train our network, but also we exploited the concept of temporal continuity, because usually the actor doesn't change heading very drastically between consecutive frames. So we also exploited this information while training. But the focus of this talk is not really this module, even though this is very interesting. Feel free to talk to us offline and ask more about this. And Wenshin, who's sitting here, was the main contributor in this part. So after we get an estimate, so these measurements of where the actor is and what's the current heading direction of the actor, we feed them into the motion forecasting module. And for this, we use a common filter with both kinematic models for people and for cars. And we have to make this separation because people can change directions and they can change velocities much more sudden than cars that are constrained by the steering angle. And this common filter works quite well in practice. So most of the times we see almost linear trajectories for the actor. So this is just an example of, in white we have the ground truth prediction, in green we have the forecast for the next few seconds. It matches quite well. But we also see a few examples with bad predictions. If the actor does a drastic turn to another side, you have this offset. And something else is, imagine you have a tree in front of the actor. Like in this case, the common filter only uses kinematic information to make its predictions. So it would predict that we would go through the tree, but in practice you would either go left, right, or stop. And this motivated us to try another method for doing this forecasts for the actor position using inverse reinforcement learning. So based on a lot of demonstrations of this off-road vehicle driving on trails, we tried to extract a reward function. So we try to extract what are the implicit costs that the driver tries to optimize when he or she is going through the trails. And this was also quite an interesting paper that we presented at Coral earlier this year. And if you are interested about this, you can also ask more details offline. But in our system, we're using the common filter and the results you'll see today. Now that we know where the actor is heading in the world, we have to think with a motion planner. And there are a few things that we have to consider when thinking about the planner. The first one is, what is going to be our state representation? Because we're going to state that's able to accurately model our quadrotor, but we also don't want to represent unnecessary states that are just going to make our motion planner slower. We also have to design cost functions that have to be accurate enough that we model the actual behavior of the director when he or she is filming. But at the same time, these functions have to be simple enough such that they can run in an onboard system. And third, we have to think of the motion planner algorithm itself. And it should be complex enough such that we can obtain non-trivial solutions in complex and challenging environments, but at the same time, it has to be able to sustain performance in real-life conditions. And some numbers that we set as targets were a frequency of about 5 Hertz for this planner to operate in, and a 10-second time horizon. And these sort of goals were set based on the velocities involved in the act of drone filming and the scale of the objects we deal with usually, like trees or piles of dirt, etc. And so I'm going to present this design choices sort of as a linear process, but in practice there was a lot of back and forth, experimentation, but I'll do my best to convey the ideas that we had. First we thought, what is the minimal state representation that we could possibly have for the system? Well, if you're filming something with a drone, you have to, at least know the X, Y, Z position of this drone in space. And you could assume, let's say for simplicity, that the heading direction of the drone is looking towards the actor at all moments of time. If we, after defining this states, we can think about a trajectory. So we say that C Q for the quad rotor is the trajectory. That's simply a concatenation of states over time. And we can think of a generic cost function that we try to optimize, function J, that tells us how a trajectory is, if it's good or bad, or how good or bad it is. And the objective of any motion planner algorithm that we come up with is going to be to find the trajectory C star that minimizes the cost function over our desired time horizon. And then, which kinds of planners could we use? We have a few big categories of planners. We can think of search-based planners first. And these planners are very interesting because they do have guarantees, if you're using the right heuristics, that you'll find the globally optimal solution in your search. However, specifically for the case of drone filming, we would have to define quite a large state representation if we're trying to use a search-based planner, involving the position, velocity of the drone, and also time. Because this is not a typical motion planner problem in the sense that we're trying to go from point A to point B. There's not really a defined goal state, because what we care about is how the goodness of a trajectory that ends 10 seconds away from now. So you have multiple goals in your search, and all the goals would be all the possible positions and velocities where you could be 10 seconds away from now. And this makes up a huge state space that you'd have to search over. And that's desirable. The second big category is of sampling-based planners. And these planners also count with very nice guarantees. If you're using an algorithm like RRT, you are guaranteed a probabilistic completeness, so you know that you will find a solution as the number of samples goes towards infinity. If you're using something like RRT star, you know that asymptotically you will find the optimal solution. But we face the same problems that we faced with the search-based planner of having quite a large state space representation. And that's also not very desirable. And the third big category is of optimization-based planners. And these planners have some interesting properties for our problem because they can obtain a reasonable solution that's going to be locally optimal, but not globally optimal, but they can do that very fast. And they can easily take advantage of a good initialization. And usually we use the solution of the previous planning problem to initialize our next optimization. And due to these properties, we thought that optimization-based planners were more appropriate for our problem. But there are many techniques inside optimization planners that could still be used. You have what are called potential fields that basically try to repel your state away from obstacles. So these are some of the first optimization-based planners developed. You have model predictive control, where you require a pretty good model of the dynamics of your system, and you optimize for both the optimal states for this optimal trajectory and for the control outputs together. But a disadvantage is that since this is quite a complex optimization operation, you end up in practice only having very small time horizons, let's say, such as half a second or maybe 1 second into the future. We also see techniques such as STOMP and ITOM, and these are methods that use stochastic variations of your trajectory to find the best directions to go next in the next iteration. And finally, we find methods like CHOMP and TRAJ-OCT that they do take advantage of gradients, and you can see that the previous methods like search-based planning and sampling-based planning only take advantage of evaluating the cost function at your samples or at your next states. But these planners here, they use more information to guide your search, or actually guide your trajectory towards these regions of low cost. So they can be slightly faster. And from those two methods, we used we modified the chomp motion planner because it had so I thought about especially the definition of the occlusion cost function, and it could be nicely derived by using some properties of the obstacle avoidance cost of chomp. And in traj-opt, this derivation is not so trivial or simple. And chomp also gives us a naturally smooth output as the solution, and it gives us the solution quite fast. And that's the rationale behind these choices. Now that we defined the state representation and the motion planner, we can go to the definition of cost functions. And the way I came up with these cost functions was by reading a lot of books on cinematography, reading some related work, and also I had talks with directors, movie directors, and with actual cinematographers to see what are the objectives that they try to optimize when they are filming. And in many cases, it's quite, for them it's quite intuitive, and they sometimes have a hard time even explaining this to somebody else. So it was an interesting process. And these functions are, the main functions that I found were obstacle avoidance, because you clearly don't want to hit anything while you're flying. Occlusion avoidance, because you usually want to have your actor on site most of the time. Smoothness, because a shaky video is not visually appealing. And the artistic intent cost, which is going to be a little vague right now, but I'll explain it in more details later. So let's take a look at the obstacle avoidance cost. The intuition behind this cost is that we want to stay as far away as possible from obstacles. And to do this, we take advantage of a concept of a definition of signed distance fields. You can see in this picture, in black, we have the borders of obstacles, and the signed distance is going to be positive if you're outside an obstacle and negative if you're inside. And the module is going to depend on how far away you are from a border of an obstacle. And we also define a penalization, so a cost, C, that depends on your, so for each point in space, we have a cost C that depends on how far away you are from an obstacle up to a distance epsilon. So if you're at epsilon, your cost is 0. If you're further than epsilon from an obstacle, you also have 0 cost. But the further you're going inside, your cost is going to increase. And in the equation that gives us the obstacle avoidance cost for a given trajectory, we integrate over the entire trajectory this penalization. And we have to multiply it by the velocity at each point in the trajectory to avoid some pathological behaviors. So imagine you have a discretized trajectory. If you try to apply this cost, try to minimize this cost without considering the velocity term, you could end up in a case where your points are going to go, let's say, right and left of the obstacle, and you'll simply have a case where your drone is going to go super fast through the obstacle. But that's not really solving the problem. You're going to crash. That's why we need this velocity term. Now, for occlusion avoidance, we also take advantage of the same concept of signed distance and of this penalization C. And the intuition behind this cost was that for a given pair of actor and drone trajectory, so we freeze one instant of time, we want to minimize the penetration of this line, of this path P that connects both positions inside of obstacles. And we wanted to come up with a function that can be used for any shape of obstacle. And let's take a look at the equation. So imagine that we freeze a path parameterized by tau. We're going to integrate the signed distance penalization over this path. Again, we have to multiply by the velocity along the path for the same reasons as the occlusion costs. And then we have to, but this was only for one pair of actor and camera position. then we have to integrate this over time as well, because we want to minimize the occlusion over the entire trajectory. So we're basically integrating the penalization of signed distance over this 2D manifold that connects the camera and the actor over time. The third one is the smoothness cost, where the intuition behind it is simple. The idea is that we want to minimize the time derivatives of a trajectory. So very intuitively, this trajectory would be better than this, that jiggles around. And what's nice about this function is that it can be represented as a quadratic cost that has an analytical Hessian. And later I'll explain why this is really important for the optimization. And in practice, we minimize up to jerk. So we minimize the first, second, and third derivatives of our trajectory. And finally, we come to the artistic intent cost. And so this cost was derived based on a lot of literature that I read and all those conversations with directors. And I tried to distill what are the, let's say, main basic parameters that define a shot when the director is filming. And these are first the line of action angle. So this represents the relative yaw between the actor and the drone. So if the drone is in front of the actor, that would be, let's say, 0 line of action angle, and so forth. We also have what's called the tilt angle. And that tells us how up or down the drone is going to be relative to the actor's horizontal plane. And third, we have the shot scale. That means how close or far away the camera is going to be from your actor each moment. And what's nice about this set of parameters is that for any position of the actor, we can define one unique position for the quad rotors, XYZ position for the quad rotor, that is based on those 3 parameters. Like we're basically placing the quad rotor using spherical coordinates around the actor. And we can do this for every instant of time in the actor's motion forecast. And we can obtain what we call the desired artistic trajectory that tells us where the director would like to be if he was trying to do this particular type of shot. And when you look at the cost function for the shot quality, it's actually quite simple. So what we try to do is we calculate the average distance between the current iteration of our trajectory in the optimization process and this desired artistic trajectory. So it's a an altitude distance, and another good property is that in discrete form, it's also a quadratic cost, so we have an analytical expression for the Hessian. And now that we defined all 4 cost functions, we can define the main cost function J, and that's simply a linear composition of all those 4 costs, and each one of them is multiplied by a relative weight lambda. And the objective of the planner is to find the trajectory that minimizes the overall cost over our trajectory. And here's where we adapt the CHOMP algorithm to work with our particular planning problem. Initially, we get a initialization for trajectory C of the quad rotor. Then the first step is to calculate this matrix called N inverse. And what this is basically an approximation of the Hessian of our cost J. And what's nice about this is that we can calculate this matrix outside of the main optimization loop. So we only do one matrix inversion here. And then in the main optimization loop, up to a maximum of Imax iterations, we check if our convergence criteria has been met. And if it has, then we just return the current trajectory. If it is not met, then we take a step in the direction of steepest gradient descent of our cost function, J, multiplied by this approximation of the Hessian function. So it's sort of almost a standard steepest gradient descent application, algorithm application. But I want to make a few comments about this matrix M inverse. So let's step away from our problem for a second. Let's think that we are trying to optimize a generic function h. We can do a linearization of function h around our current optimization point x. But usually these linear approximations are only good within a small region that we call a trust region around point x. And when you're trying to find the optimal step to optimize function h, you will have this trade-off between how far down the gradient direction you want to go versus how close to the current point x you are. Because the further you are, the less you can trust that approximation. And you use this metric d to tell you how far away you are. If this metric d is the Euclidean norm, you end up with the vanilla definition of the gradient descent algorithm. So you take a step size alpha in the direction of the gradient of h. But in practice, you could actually use any valid norm for function d. And specifically, you could use any measurement definition from the Mahalanobis metric. And if this matrix A here, that's what provides you the metric, was just the identity function, you end up with the Euclidean norm. But and if you try to optimize this equation here, using d as this definition, you end up with the inverse of matrix A, multiplying your gradient of the function. And in our case, we use that matrix M inverse to be the inverse of A. And what's nice about this is that we end up with a covariant definition of our gradient steps. It's called covariant because it doesn't matter how we parameterize our trajectory. We could parameterize it as x, y, z. We could use, let's say, spherical coordinates to parameterize our trajectory. You make sure that if you use this metric, you will take a step of the same size during your optimization. Because if you're using, let's say, spherical coordinates, your Euclidean metric is going to be different than if you're trying to use the XYZ metric, for example. And now that we understand the optimization algorithm, let's see some results of our method and take a look at the system. In terms of hardware, we use a DJI M210 drone with a Zenmuse X4S camera and a NVIDIA TX2 computer to do all the calculations. And in some of our earliest experiments, we had a helmet on the actor, as you can see in this picture, with a PX4 device that had a GPS and a compass to give us the localize and give us the orientation of the actor. But then we got rid of this device when we moved on to the purely visual localization for the actor. In terms of some general statistics, in a typical flight test, we can fly for about 25 minutes with a battery. The planner is operating at 5 Hertz with a 10-second time horizon. The detection of the actor in the images takes about half a second, but then after we get the first bounding box, we can track the actor at about 15 Hertz. And specifically for the paper we presented at ISER, we collected about 2 hours of footages with the system, but overall in this project we have collected many more hours. And this is how a typical flight test goes. We have this pre-mapped environment, and the actor can go in any path he or she desires, and the drone is going to execute the desired shot type while avoiding obstacles for safety and occlusions. This is what the motion planner sees. So it sees the current actor position, the forecast, the desired artistic trajectory, and this is the current trajectory being executed. And here on the right side, you can see the view from the camera of the drone itself. We also have done tests comparing the impact of the occlusion cost function that we introduced. In this first row, you can see how a test goes if we do not take occlusions into account. You end up not seeing anything in the image. You won't see the actor. Because the mountain, even though you're not colliding with the mountain, it will be in front of your camera. But if you do take occlusions into account, you make sure that your drone always has the actor on sight, and we find it is very nice and smooth trajectory above the mountain that tries to stay as close as possible to where the director would like to be, but avoids occlusions. We also have field tests with different types of actors and different types of shots. Here we do a circular shot around a person. We have a right side shot with a biker, and a left side shot with this car in high speeds. And we also have quantitative results where we compare the power or the role of the occlusion cost function in the optimization. So we have this simulated environment with a bunch of spheres which are randomly placed, and we did tests looking at two metrics. One is the actor visibility along the trajectory, and the other one is the average distance to the desired artistic position. And you can see that as the number of spheres in the environment goes up, we can see the actor less. But if you do take occlusion into account in your cost, you will have a much better performance in terms of seeing the actor compared to if you don't take occlusions into account. But the trade-off here is that since you're avoiding occlusions, you may be much further away from the desired artistic position. Now we can go to the conclusion of this talk. So in summary, in terms of motion planner, we show the development of a motion planner that can plan trajectories in real time with these non-myopic forecasts of the actor's trajectory. And also it can avoid arbitrary shapes of obstacles for both obstacle avoidance and occlusion avoidance. Second, in terms of the vision pipeline, we are able to automatically detect and track and localize the actor in space and estimate the actor's heading at each moment of time. And third, in terms of artistic capabilities, we are able to film these actors in real life outdoors environments, even when we have a lot of noise in the localization of the actors, and follow as closely as possible the director's artistic intents. And here on the right side, you can see a few of the shots that we generated with our system. So in this case, we're tracking a biker circling around him. We're not hitting the mountain. And we have a lot more footages that, if you're interested, you can see. And in terms of next steps, so something that I mentioned before was that since we're using a optimization-based planner, we are finding regions of local minima of our cost function in the cost landscape, and we're trying to see how we can learn initializations and sets of relative weights so that we can achieve the actual or be closer to the actual globally optimal cost for our trajectories. Also, something we're looking into is how to learn from demonstrations of good footages the director's true artistic intent and true cost functions that he or she tries to optimize with intuition. And third, we're looking into how to automatically choose the right types of shots for each given environment. So for a particular environment, you may want to do a right side shot because this is going to avoid obstacles more easily, this is going to look nicer. So we're looking into how to learn these shot selection from demonstrations. And lastly, I just want to thank the amazing people I was able to collaborate with and also discuss research ideas in the past years at CMU. You have been very helpful towards my project. And thank you very much.
So you don't have to do it. I mean, if you have some questions, for sure.
Maybe start with
yeah. Oh, you can turn it back on. Okay.
Hey, David, I think we can start with, if you have any questions, you can ask them, or... Oh, good.
So a few questions. participant intent. I think you mentioned like yaw and tilt. Did you also include zoom in that? Or?
Yeah, so that was a design choice that we made, not to include the zoom. What we do if we want to change the like how close or far we are from the actor is we change the shot scale, so we would physically be closer. But for this version of the cost function definition, we don't include zoom.
Okay, that's fine. I was also wondering a little bit about, you said you talked to cinematographers. Do you have any sense of what type of input they normally like to provide for controlling these kind of persistent parameters? Like, would they want to specify like a yaw and tilt angle, or is there some other type of input that's kind of more intuitive to them?
They usually, so when I define the artistic intent cost, I try to use their terminology. So they do use they call it line of action angle, the tilt angle, and the scale. So they do use these parameters. And like something that actually they said it's really important, but I don't have in this work, is they said lighting, the light, how the light is scattered over the scene is an extremely important factor. But for this paper, we don't have that included.
Interesting. And I guess a related question, sort of just curious on the tying into the application side for movie making. Do cinematographers usually like these parameters to be fixed over the course of a single shot? So like you always want to have a single sort of angle that you're tracking the target for the whole shot, single scale, things like that, or do they sometimes want to vary these, like zoom into the target and things like that?
It varies a lot on the application. So the question was, do those parameters usually, I don't know if everybody can hear, but do those parameters for the shot usually remain constant over the scene, or do they change? And I think it depends a lot on the application, because if you're doing a very scripted scene, let's say you're filming a commercial for a product, for a car, then you might want to change those parameters over time, but they would be very predefined. But let's say you're filming a person snowboarding in a mountain. Usually you would want, so this is not really a scripted scene, but you would want the parameters to vary over time so that your shot is not boring. Because if you keep the same parameters the whole time, you're going to lose some visual appeal. That's why usually you want to change those parameters to keep the attention of people who are watching.
Okay, that makes sense. I guess another question also kind of similarly, have you thought about how you might extend this to, let's say if there's multiple actors that you want to track, like in a sports, a team sports scenario?
Yeah, so we actually ran a few, so right now our framework only receives one actor as input. We tested we did a few tests where we had multiple people playing soccer with one ball, and so whenever we lose confidence in the tracking of an actor, we redetect actors in the image, so it's sometimes like switched between people. But another very interesting and different problem formulation would be if we have actually multiple people, should we film, let's say, a centroid of whoever is playing basketball or soccer? But so I have thought about it, but I haven't actually like done these kinds of experiments yet.
Okay. Yeah, that sounds good. Thanks.
Okay, thank you.
Yeah, I can go next. I think as we've spoken about in our offline talks, I like the topic. I think it's cool. I haven't seen too much on it, so I think that's always a nice thing to have sort of a topic that's sort of neat. I've got a nitpicky thing. On slide 41, I think, I was confused a little bit You're at 41. Again, just nitpicky. I was confused. Why? Yeah. We'll go forward to 42 actually. Yeah. Why is that the trace? Because if that's a vector, if delta Q transpose A shot, why is there a trace there? Trace is typically applied to a matrix. That's a scalar output. Why is there a trace around that?
It's because this trajectory here is defined as x, y, z.
X, Y, Z. So is X, Y, Z, is this a big vector or is this a matrix?
So I have x, y, z for each position in time. So I have x, y, z.
All right, so that's a matrix. Okay, so I was all right. So if that was a vector, okay.
Yeah, sorry, yeah.
Okay.
So this
all
thing,
right.
C is a matrix.
And then are there any constraints on that, or is it there's no constraints on that? They're allowed to be real. It's constrained to be like a real valued set. Are there any constraints on that?
On what the trajectory C can be?
Yeah. Like if you're feeding this into, you're saying that I've got a closed form deterministic. That's true if there's no constraints on that. But if it's constrained, then that's not true. So are there any constraints on that?
No, it could assume any real value of x, y,
cool. So that was jarring. It's a little nitpicky thing, but that's good.
So I actually have a related question, maybe just to follow up, is so this A shot, so this has to be recalculated every time you solve it again?
At every planning problem, but not in the main optimization.
Sure.
Yeah.
But there is a little, so this A, so what is, so how do we actually get A shot here, and B shot and C shot?
So what I did was I went from this definition, then I created a discrete integral of the cost function, and then I had to manipulate, so I had to create matrices that I called K and E, such that I would have a matrix multiplication. Like if I took the trace of this operation, then I would have the same original function. So I sort of did some reverse engineering to get A shot, such that if I did this operation, I would have the same value that I see here for my cost. I didn't include all the math, but I.
Okay, so what kind of operations are necessary to get A shot? Maybe just in a high level, like how much math do you have to do? Like how many calculations and what are the sizes?
Yeah. Basically, what I defined was.
Is it like, for example, specific to a certain choice of trajectories, or is it like you just get A shot once and then it goes for all combinations?
So A shot is going to be dependent on what is the C shot. C shot is the desired artistic shot.
Mm-hmm.
So A shot is going to be actually solely dependent on this value of C shot.
Right. So A shot is basically you take the trajectory and turn it essentially to a matrix that if you multiply the desired with, it gives you some error essentially, right? Like some L2 distance.
Correct. Yes.
My other bit of feedback too on this is that personally, again, it's all a matter of taste. Personally, I hate computer science talks that have integrals because unless you are explicitly defining that integral, so if you've got a continuous function and you're explicitly finding the solution to that integral, it has no business being on the slides. Because you, at code time, when you're coding this up, you're not coding up an integral, you're coding up a summation. That should be the objective. I find when people write papers or do other things, they're trying to obfuscate, they're trying to hide things when they do integrals, because that's really hard to follow, that's easy to follow. So I'll go from now on, unless there's a real reason to have an integral, don't use it. People get in the habit of doing it because they say, oh, I'm going to try and lose people and do other things. But integrals make sense if you want to explicitly solve that integral. Okay, if it's a continuous function, you're doing that. But if you are saying, well, actually, a discrete form, it really is a discrete form. You're never ever solving that at code time. Correct?
Yeah.
Yeah. Don't do it. It just confuses people.
Yeah. You're going from the definition and then.
Yeah. Still, I think we can follow that. that is just sort of like, all right, well, what's going on?
Well, I
To be honest, I find
actually,
that to be more
actually,
easy to
I mean,
follow.
actually, the left one I can understand. The
Yeah.
right one is actually quite tricky.
Exactly.
Because
It's the
it's
same
not
problem.
obvious what A shot
Yeah.
and B shot and
But
how
you can
it's-
see how that's solved. I mean, anyway, it's a matter of taste, but I'd say like, if you're not doing it, you're not doing that. You never actually do that.
Right.
You do this.
But if I look at this, I can see, okay, he's trying to
Trajectories.
integral of the difference in trajectories.
Yeah.
The right side,
Yeah, but if you get, anyway, we'll get to the separate thing.
That's
But
why
if you actually do those with computer science, they never implement it that way. They do that. But
That's why I have
all right.
both to please everybody.
Yeah.
Merit taste. The other thing too is that I said like now more broadly, I like the end part when you're talking about sort of like learning the directors, learning from directors and learning that. And I've been curious on sort of like some directions on that, because one thing that strikes me is sort of like in computer vision, a really popular thing at the moment is the use of conditional GANs, like people kind of sketching things and then actually kind of doing things. Okay. I was wondering now, that's easy because that's in batch. So I don't know, are you guys thinking something similar here? Because that's what I would have liked to kind of like hear a little bit about, because I think that's the real challenging part here. How do you, like, if I was a director and I'd say, all right, I'd sketch out roughly, this is where I like my drawing to go, and then just speed it over, and then it could just go.
Or maybe
go,
like use
go
storyboards.
like pix to pix or
Yeah.
things like that. Like,
this.
That's a cool idea.
yeah, so like,
That's
is
a
that,
storyboard.
are you thinking like that, or what are you thinking with respect to that? Because you just sort of had a bullet point learning that, but, and you don't have to present it, but like, what are you thinking?
So, I think there are different problem formulations when you, so,
We lost David. He didn't like my integral statement either.
Okay, he said check. He has to run for a meeting.
No problem.
Ask,
Thanks, David.
to check the email. I guess
Thank you.
he sent you an email.
Yeah, he has a meeting.
Okay.
Yeah, that was just my other thing. Well, but if you haven't thought about it, I think conditional GANs would be an interesting thing to look at. And then following up on that, just let me download the last bit, is that I think maybe going ahead, you should try to partition what you're doing into kind of two parts, because obviously in the final system it has to be real time and kind of moving. At the moment, you've kind of coupled, like I would be interested in sort of like, all right, well, what is sort of like the optimal system if you didn't take real time into account? If you kind of just did batch and you kind of just said, all right, if I'm going to do this in a simulator, I've got all my samples, everything, what does that look like? And then how do I make that kind of real time? At the moment, you kind of, it's kind of linked, and I know why, because at the end of the day, that's what you want. You don't want a batch system. But I'm just wondering whether you're skipping over some neat ideas that could help you to kind of beef this up. So that's my other bit of comment. I like the talk, I like the direction. I had a question over that, but they were my comments.
Yeah, but I think you talked about very interesting points, and so in terms of the first question you asked, like how, like you said, oh, should the director try to like make a sketch of roughly the kind of scene he or she wants, and then the drone figures out what to do from there? That's a possibility. I think the way we were thinking about learning the artistic intent was more towards full autonomy of the drone. So like based on features of the environment, and these features are for now loosely defined, we're still trying to formulate this problem, then you would just find the best kind of shot or the best direction to go to. The how to do it, we thought of GANs. We thought a lot about inverse reinforcement learning and do something similar to what we did for the learning the cost functions of the car, but doing that for the drone. I guess GANs and IRL are linked, right? There are some papers that make this connection, so they're behind the scenes, sort of the same thing. And I think that's the direction we plan on going. For now, I think it is loosely defined, and we're trying to figure this out.
I mean, my only other last comment on that is that sort of with all this stuff, it's kind of subjective too, and sort of like guiding yourself through that minefield a little bit, and sort of like, well, how do I know? And you've got metrics and other things like that, but that's the other thing I just sort of mentioned to you to think about more is sort of when people dabble into this, is sort of like trying to not get too subjective. And so, so like thinking about how can I make sure, so like, does this really look like that artist? And oftentimes people just end up looking at images and all that. So I don't know, visualizations or how like this is how this director would do this. from what you're saying, that'd be harder to do. I don't know, but I love the direction, but I think that's going to be challenging. I think doesn't mean it's not possible. It's just going to be challenging. I think. But cool. I like it.
Any other questions? Yeah. This is a planted question or a hard question?
No, the question we agreed on.
So you said you wanted to use an optimization that considers the global minimum, but I wonder if your function has more than one minimum. So have you run anywhere in practice where the minimum you found is really not good, and you had a global minimum that was better, but your local algorithm didn't find it?
Yeah, so if you think of, let's say the simplest obstacle you'd find in real life, a tree. So if your actor is going on one side of the tree, like your possible modes would be, let's say, to go above the tree, go in front of the tree, go behind the tree. All of them could possibly be, or maybe go below the canopy of the tree. All of these would be regions of local minimum. Our algorithm is going to be like super dependent on the initialization that we have for the optimization problem. So if we, yes, like we're always finding local minima of this function, and to actually know where the global minima would be, we would have to sort of brute force search all the possible trajectories, which we don't do in runtime.
But have you done that offline for one particular case, just to check if there are how bad your local solution really is?
Yeah, that's the sort of thing we're investigating right now. So I'm working on if I actually had a offline brute force like searcher of trajectories, could I actually try to learn how to initialize my planning problem, such that I can get closer to the local minimum, depending on the features of the environment. So it's something I'm like actively working on right now.
I actually had a few questions.
Sure.
So tying into what Simon had said and based on some of our past discussions, so one of the questions I had was, have you thought more about trying to evaluate how well your system is working, looking at just the images themselves? So if you recall, so right now you've got all this framework where you're moving around, but how do you, have you thought about photometrically figuring out that, oh, this is truly the sequence of the video that I finally got is along the lines of what my director wanted, so that, for example, is the face in the final video ending up in the location that I wanted to, and try to use that photometric cost function as driving some of the optimization. And because that fits in fairly well with things like trying to match well with what the director's intent is. And then there's all sorts of fun things that you can do. Then you can train against different kind of footage, so you get the style transfer or what have you.
Yes.
So you've got whatever Kowalski style, or you've got Spielberg style. So have you talked more about that?
Yeah. So we have we went in this direction for a little.
It also works very well with simulations. So
yeah, in these results, we do compare the visibility. So how much of for how long of a trajectory are you actually seeing the actor, and the average distance to the desired artistic shot. So this is a metric that we computed. We don't have statistics on. So we also choose on the gimbal, for the camera, is the actor centered or not centered, but on the desired screen position. We could compute this metric, but we have not obtained, we haven't calculated those statistics.
Right. But this distance here is just the XYZ difference.
Yes.
Right, it could be that you're off by a couple meters, and it's still artistically fine, or it could be that you're right on it, but it's not a great shot. Right, I think.
Or you could have a leg of your robot in the shot, right? For example, you had some of the shots where you move doing this fancy bank movement. When suddenly a leg of the quad rotor or hex rotor comes in, right? And ideally you don't want that in a shot, but there's nothing in this geometric cost function that's going to prevent that, right? So because at the end of the day, you care about what's actually coming in,
I think the true metric would be a metric of beauty that a user evaluates. We have not done user studies with this system, but we could potentially do that, and so either have labeled data from user studies or just get demonstrations from good footages. I think those are the two directions that I think could matter, where we could solve the question of obtaining the true artistic costs that people try to optimize themselves.
I had just one more clarification question. So for your heading stuff, right, when you're trying to detect heading from images, my question was, since you know where your quadrotor is, and because you're using a fixed focal length, do you really need to go through this effort of throwing it to CNNs where you can get a primitive estimate of what the motion is using just projective geometry? Right, because you've got bounding box detector, you know how tall or how big humans generally are. So given a temporal sequence of detections and the fact that you know where your camera is and the pose is, one could assume that you could figure out what the heading direction is anyway.
I agree you could do some calculations to avoid detecting the heading explicitly, but in case, especially for people, since like you could be just moving, in place.
That's right.
Then in this type of case, you would not know where the right side is, for example.
Okay.
So for this kinds of situations, and like, people would also walk sideways, that's
Okay.
why we.
I think that's fair. One final clarification question. I think slide where you showed the assigned distance field thing, I was slightly confused because the cost function I saw versus the illustration I saw didn't, and the explanation, so one side differs. Yeah, so you're saying that, okay, you said inside the obstacle, the cost function keeps increasing, right?
No,
And-
inside margin epsilon, that is
Yeah.
outside of the obstacle.
Right. After epsilon, it should be 0.
Yes.
But I was very confused because when I was seeing the cost function outside the obstacles, the cost function is increasing to 100.
Oh, sorry. This is the actual value of the signed distance,
Right.
and this is the parallelization of the signed distance. Like this is the value of d. This would actually be a c of d. Actually, maybe this notation is not the best, but like you would get a value of 100 over there, and you would go into the x-axis of this plot, and you would go to like 100, and that would be pretty far away from epsilon, and this would be 0 cost. So this.
Oh, so this is not the visualization of the cost.
Yeah, this is not the cost. This is the
Okay.
visualization
Okay.
of this
Okay.
signed distance.
Okay. So I thought this was slightly confusing. Threw me off a little.
Okay. I agree. I should improve this. Visuals. One more question.
Yeah, how do you determine your lambdas, and I guess like how sensitive is your algorithm for different types of actors with respect to the lambdas?
The way it determined was mostly in simulation. I was the human optimizer in the loop, and I tested a bunch of values for lambda that provided good motions for the drone in the type of environment that we were operating in.
And so is it different for each type of actor or type of shot, or is it just, one set and it more or less works for different types?
Right now it's one set for, like we have the outdoors environment called Gascola. So I selected one good set of weights for Gascola specifically.
Okay.
If we go to another environment, then I may change the
So
weights.
it's environment dependent, not actor dependent.
It also has to do with the actor itself. I was testing those sets of weights for the already, like I was in simulation. I could simulate the actor walking or a car being
But it's
driven,
not very
and
sensitive.
like I selected a set of weights that would work well both for people and cars in low and high speeds. But something that we're also looking into is how we could have adaptive weights, like in the same line of idea of trying to achieve the global minimum of the cost. Like how could we change the weights such that we can go to the global minimum instead of, or get closer to a better shot. But then of course we need this external evaluation
But
function.
your global minimum is a reflection of the cost function, right? So if your cost function changes, that also changes.
Yeah, so we would have to define a external cost function.
Photometric.
Yeah, that we could evaluate
Okay.
different planners of different
I see.
relative weights from the artistic intent of the director.
Okay, thank you.
Thank you.